is the last little piece of our mole unit. This is all about hydrates, hydrated compounds. Hydrated compounds are compounds that attract water molecules from the environment. Now, these notes and homework are same page because the notes that are embedded here on this homework, they're really good. So I'm just going to use these as the notes and the homework. So you'll find these on pages 17 and 18 in your homework packet. Okay, so that's where you need to be for these notes. So hydrates. A lot of compounds attract water from their environment, and those are called hydrated compounds. If we were to heat it up and drive off all the water, then we would call that an anhydrous compound. That means without water. Okay, but this specifically, we're going to talk about hydrates, hydrated compounds, compounds surrounded by water molecules. To name them, you're going to use the same prefixes for the water molecules as we used for our covalent compounds. The way you'll see a hydrated compound, you'll see a formula, an ionic compound, and then there will be a big dot there, and then there will be a number in front of water. Okay, so you name this first compound exactly the same as you would. This is sodium sulfate. Okay, but then when you see the dot followed by the number of water, that means that there's 10 water molecules that are surrounding this sodium sulfate. So the way we name this whole thing is sodium sulfate decahydrate. Deca is the prefix for 10. So it's sodium sulfate decahydrate. Okay, the prefix will go in front of the word hydrate for the water. Okay, the naming rules for the ionic compounds will be exactly the same. If you have to find a Roman numeral, that's hard, but that's the way it is. You know, sometimes you have to do that. So I'm going to name these 4 down here, and then we're going to do the molar mass for one of them. So strontium is not a transition metal. It's a metal, it's in group 2, so this is an ionic compound. And since it's not a transition metal, it doesn't get a Roman numeral. You just name this thing. So this is strontium chloride. Then we use the prefix for 6, which is hexahydrate. Okay, this zinc is not it's a transition metal, but it doesn't have a Roman numeral. It's an exception. So this is zinc sulfate. Then we use the prefix for 7, which is heptahydrate. This one here, sodium is not a transition metal, so this thing you just name it sodium carbonate. The prefix for 10 is deca, and then the word hydrate. Okay, manganese is a transition metal. Okay, it gets a Roman numeral. So we have to uncrisscross the subscripts and make them into oxidation numbers. So that 2 goes up there with a plus in front of it, and there's an understood 1 there that goes up by chlorine with a minus. Okay, chlorine's oxidation number is -1, so that means manganese is definitely positive 2. So this thing would be manganese. This is going to be a long one. Manganese 2 chloride 4 is tetra. See, it's up here, tetrahydrate. All right, so let's do the molar mass of this thing. What I want to remind you first is the molar mass of water, because you're going to treat water as a single element. Okay, the molar mass of water, 18.015 grams per mole. Okay, and that's going to make our job a little bit easier. So to do the molar mass, we start out manganese times 1 and chlorine times 2. And then we're going to do water times 4, because we know the molar mass of water. So manganese is a transition metal, and it's right here, 54.938. 54.938 because it's just times 1. Chlorine times 2. Chlorine is 35.453, and I have 2 of them, so that's 70.906. And then water times 4. This is going to be 18.015 times 4. .06. So to find the molar mass, I add all of these together. 54.938 plus 70.906 plus, what was it, 72.06. And I get 197.904 grams per mole. And that is a molar mass of manganese 2 chloride tetrahydrate. Big, lots of words. Okay, so this next section, we're going backwards kind of. We're given this molar mass, and we're asked to find that. Okay, you're going to have to find the number that goes in front of the water. How many water molecules? Okay, not as hard as you may think. First thing you need to do for all of these is you're going to have to find the molar mass of the compound first. Okay, this is the molar mass of the whole thing. First I need to find out the molar mass of copper 2 chloride. So it's copper times 1 and chlorine times 2. Copper's molar mass, let me pull over my periodic table for you, 63.546. And chlorine times 2, well, we did that up here, so we're just going to steal that, 70.906. Okay, the whole thing is 170.49. That is the copper 2 chloride. So let me add those together. 63.546 plus 70.906. It's 134.452. 134.452. So I'm going to subtract the mass of the entire compound from the mass of copper 2 chloride because the rest of it has to be water. So 170.49 minus 134.452. Let's see what that is. 70.49 minus 134.452 gives me 36.038. That's the mass of my water. I just need to find out how many waters that is. So I take the mass of my water and I divide it by the molar mass of water because we're finding moles. 36.038 divided by 18.015. It's 2. So my N value here is 2. This is copper 2 chloride dihydrate. Alright, let's do the one down here because I need some room. Need a lot of room here. Okay, given that the molar mass of magnesium acetate, some number of moles of water is 214.46. First step, find the molar mass of magnesium acetate. Okay, so that's going to be magnesium times 1. How many carbons are there? 2 times 2 is 4. How many hydrogens is 6. And then oxygens is 4. So let's find the molar mass of all these things. The molar mass of magnesium is 24.305. Molar mass of carbon is 12.011, and we have 4 of them. So 12.011 times 4, 48.044. The molar mass of hydrogen, 1.008. times 6, 6.048. And then oxygen is 15.999 times 4, 63.996. Okay, so let's see how much of my compound is magnesium acetate. Okay, because the rest of it, the difference between this and the mass of this is the mass of my water. That's going to help me out a lot. 24.305 plus 48.044 plus 6.048 plus 63.996 gives me 142.393. 142.393. Okay, that's the mass of magnesium acetate. That's the mass of my whole compound. The difference between these two is the water. So 214.46 minus 142.393 is equal to, let's see, 72.067 is the mass of my water. So in order to find the moles, or the N value, the moles of water, I do 72.067 divided by the mass of water. And it's 4. So my N value is 4. It's a tetra. So it's magnesium, oops, sorry, husband. Magnesium acetate big dot 4 H2O's. Okay, so this thing is magnesium acetate tetrahydrate. What do you think about that? Lots of math, but it's math you can do. It really is. So let's go on to these next ones. So we're going to do an empirical formula. Let's do this one right here because it's in the middle and I'll have plenty of space to write. So we'll do number 11 here. So we're going to do the empirical formula for this hydrate. Well, I know that 18.505% is water. So we're going to start out empirical formula. So remember, it's percent to mass, mass to mole, divide by smallest to make whole. So I'm going to turn each one of these into grams. Okay, chromium. 17 point, yeah, let's do it a different way. Do it the way I had been doing it. 17.804 grams of chrome. And then, let's see, I think I'm going to run out of space. 14.388 grams of nitrogen. 49.303 grams of oxygen. And 18.505 grams of water. Okay, so I need to go percent to mass, which I did. Now mass to mole. So I need to divide each of these by its molar mass. Molar mass of chromium, 51.996 grams. Okay, so let's see how many moles that is. Uh, 0.3424. 0.3424 moles. Then we'll do nitrogen. Divided by the molar mass of nitrogen. It's 14.007. .388 divided by 14.007. 1.027. 1.027 moles of nitrogen. So let's do oxygen. I'm going to divide it by the molar mass of oxygen, which is 15.999 grams. Let's see. I'm trying to make it where you can still see it. There we go. You can see that. 49.303 divided by 15.999. 3.082. Let's go 3.082. 3.082 moles. And then water. Remember what the molar mass of water is? So 18.505 divided by 18.015 gives me 1.027 moles. 1.027 moles. Okay, so what have we done so far? Percent to mass, mass to moles, divide by smallest. Well, that one. Oh, just kidding. That one's the smallest. So I'm going to divide each one of these by 0.3424. 1.027 divided by 0.3424. We're going to go 3 with that. 2.999. We're going to go 3. Okay, this one, 3.082 divided by 0.3424. Nine. We're definitely going 9 with that one. And then this last one, 1.027 divided by 0.3424. We're going to go 3 with that one. Okay, so these are subscripts. That is the prefix for water. That's the number of moles. That's a prefix for water in this hydrate. So this thing is going to be Cr, chromium, with a subscript of 1, nitrogen with a subscript of 3, oxygen with a subscript of 9, big huge dot, 3 H2Os. Okay, something you guys may or may not notice, pay attention to. If this thing right here, if the N and the O were reduced, let's pretend, just pretend for a minute. If we reduce these, what would that be? Both of these can be divided by 3. It would make it what? It would make it that. So, couldn't we say that that's the right thing? Because it makes more sense, right? NO3 nitrate, 3 nitrates. That's 3 nitrates. So I don't expect you to go there, but I want your brain to be able to go there. Okay, I want your brain to go, all right, yeah, okay, that makes sense. Try hydrate for this one. All right, let's see, let's go ahead and, wow, let's do the last one because you're not going to want to do the last one. You're going to skip it. I don't want you to skip it, so I'm going to do it. In lab this week, one lab group finds, oh, that's weird. I think that's supposed to be finds. One lab group finds that their crucible and lid had a mass of 42 grams. So crucible and lid, 42 grams. Upon adding some turquoise crystalline substance, perhaps the total mass would become 49.49 grams. When the crucible was heated with the substance safely trapped inside, steam rose out from under the lid. When measured again, the new mass was 46.788 grams. The remaining substance was put through more tests revealing 1.906 grams of copper, 0.96198 grams of sulfur, and a collection of oxygen gas in a test tube that cannot be measured on the simple analytical balance in your lab. What amount of oxygen was collected in the test tube, and what's the formula for the hydrated compound? Oh, you for sure wouldn't do this one. Okay, first things first. The crucible and the lid, I don't care about that. That's not part of the chemical. It said that after I put the blue turquoise crystalline substance in there, my mass is 49.49 grams. So if I take this minus this, I'll have the mass of my turquoise crystalline substance. So 49.49 minus 42. 49.49 minus 42 gives me, I'm going to change pencils. That one's getting dull. 7.49 grams, and that one's going to break. So there we go. That's 7.49 grams is the total mass of this crystalline substance. Well, it said that when it was heated and measured again, I had this much. Gas came out, okay? It's 46.788. So let's see. It says it is a hydrated compound. So let's see, 7.49. So if 46.788, I need to subtract out that crucible and lid. So 46.788 minus 42. 4.788. 4.788 grams. Okay, so that's before heating. That's after heating. I happen to know that out of this right here, 1.906 grams of it's copper, 0.96198 grams is sulfur, and the rest of it's oxygen. So I have 4.788. I'm going to subtract out the copper, 1.906. So that's the copper. 4.788 minus 1.906 grams of copper. It's 2.882. Okay. Also know that I have some sulfur, so I'm going to subtract the sulfur out of it. 0.96198 minus 0.96198. 1.92. That's 1.92002. So that's the sulfur. Okay, so that is the oxygen. Okay, because I know that the solid, I had 4.788 grams of solid. Okay, that's the difference. Okay, 1.92002 grams of oxygen